Okay, so here we have the recursive call that we were actually talking about at the end of part C, where instead of just passing in n-1, we're now passing in n divided by 2. So we're basically halving the argument size. And then we have a for loop, okay, which is the exact same thing as before. So again, we can say the worst case is when P of in always evaluates to false, making us go through every iteration of the for loop, which is going to result in theta n amount of work for the recursive case, excluding the recursive call. And then the best case is when P of in always evaluates to true, in which case we're just going to break out of the for loop the first iteration, and so that's going to give us a constant amount of time. And again, assume that h of in is a constant time call, and so it's not going to affect our runtime very much. Okay, so really what's left is drawing the recursion tree for this one recursive call that we make. Okay, and we make this iteratively, not just once. So again, we start at n, we go to n over 2, we go to n over 4, etc., until we get down to 1. Now, what is the height of this tree? The height of this tree we can find by doing n over 2 to the k equals 1. And so the reason I set up this formula, or how I got this formula, is by thinking, okay, how many times do I need to divide n by 2 in order to get down to 1, right? So this k here is going to be the depth of our tree, right? Because it's going to represent how many times we actually created nodes for every time we divided n by 2. So to solve this equation, I just need to multiply both sides by 2 to the k, which is going to give me n equals 2 to the k. Then k is in the exponent, and so I need to bring it down by applying the log on both sides. And so log n is equal to k times log 2. And in general, in computer science, you can assume that a logarithmic function has base 2. And so if it's a log base 2, this is actually going to cancel out to be just 1. So that leaves us with k equals log n. And that is how we know that the depth of our tree is log n. And that corresponds to all of this. Okay, and remember the formula that we had in part C, where it was I equals 0 to the depth of the branching factor to the I times, I'm going to squeeze it in here, amount of work done per node per level. Okay, so this is a little bit more detailed than the last formula for part C. Okay, so basically if you want to apply this here, our depth is, again, log n. Our branching factor is just going to be 1. Okay, so that's really not going to matter much. And the amount of work we do per level is actually going to be dependent on the size of n at that level, right? So here at the very top, the root, the size of n is n. But the size of n is n over 2 here, the size of n is n over 4. So basically the size of the argument that we pass in halves by 2 at each level. And so that corresponds to, in the worst case, it's going to correspond to theta of n over 2 to the I. And the best case is just going to be 1, right? Because 1 doesn't depend on n, so it's always going to be 1. So this is going to be our worst case scenario. And for our best case, it's going to be I equals 0 to log n of, again, 1 to the I times theta of 1. Okay, so let's solve each of these formulas. I'm going to solve the best case first because it's a little bit easier. So this is just equal to I equals 0 log n of theta of 1, which is equal to log n times theta of 1. And you can put log n inside the parentheses to get theta of log n. So that is your answer for best case. All right, and now we get into the worst case. So the worst case is going to be a little bit more complicated. We can ignore this part because it's always going to be 1. So we can just say that this is equal to I equals 0 to log n of theta of n over 2 to the I, okay? And if I want to expand out this summation, it's going to be theta of n over 2 to the 0, which is basically n over 1, which is n, plus n over 2 to the 1, which is n over 2, plus n over 4, plus all the way to n over 2 to the log n, which is n, which is 1, right? Okay. And now let's actually let's factor out the n. So we're gonna get, oh God, this is gonna be really complicated. I'm actually just gonna delete this whole thing to see if that gives me more room. Okay, so this is going to be theta of n. I'm factoring it out. So 1 plus 1 over 2 plus 1 over 4 plus all the way down to plus 1 over n, right? So if we have, so this is a finite geometric series, right? And so the formula to find the sum of a finite geometric series is basically a1 times 1 minus r to the n over 1 minus r. And a1 stands for the first term in your series, and r stands for the ratio. In other words, what factor you're multiplying each term to get to the next term. So in our case, a1 is just going to be 1. That's the first term in our series. And then r is going to be 1/2, because if you notice, we're multiplying 1 by 1/2 to get 1/2. We're multiplying 1/2 by 1/2 to get 1/4. We're multiplying 1/4 by 1/2 to get 1/8, and etc. all the way to 1 over n. Okay, so this is going to be theta of n times a1, which is again 1. I'm not going to write that. 1 minus the r, which is 1/2 to the n, over 1 minus 1/2, which is 1/2. Okay, so sorry, I think I messed up because, yeah, I messed up because here n stands for basically the upper limit on your summation, which is log n for us, not n. So actually this is going to be log n instead of n. Okay, right there. Okay, so if we keep on simplifying this, this is going to be n times 1 minus 1 over 2 to the log n. Remember, log is base 2, so this is going to be 1 over n over 1/2. We can actually get rid of 1/2 because we don't care about constant factors in the long run. So now this is going to give us n minus 1, right? If we distribute n to both terms, which is basically equal to theta of n. Whew, that is a lot. And so that is going to be our worst case. So I guess the main takeaway from this question is just to be familiar with the finite geometric series formula, and also, you know, making sure that you understand how to differentiate between worst case and best case. It often comes in when you have something like an if statement or like a break statement, basically a possibility of early termination. And then also this formula is pretty useful. This is basically how I try to find the runtime of any function. And yes, asymptotic analysis seems and probably is a lot more mathy than you suspected. But really it's just a matter of plugging and chugging into this formula. So if you just have this on your cheat sheet, or if you have it somewhere accessible when you're taking the exam, I think you'll be good, as long as you know how to actually apply it. And then being able to draw out the recursion tree, which was very helpful for you to visualize how the function is executing. And then just making sure that you're being meticulous with your math, because there's a lot of room for error. But yeah, that's it.